Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 2, Section 1, Chapter 5, Topic 3. Understanding Impedance Variation and Voltage Droops in Switching Circuits. Introduction. In electronic circuits, impedance variation and voltage droops are common phenomena that occur when circuits switch between different states. These fluctuations in voltage and impedance can have significant implications for circuit performance, signal integrity, and power delivery. This overview explores the variation in impedance as a voltage fluctuation with time, known as voltage droops, during circuit switching events. It discusses the underlying causes of voltage droops, their effects on circuit operation, and techniques for mitigating their impact to ensure reliable and efficient circuit operation. Impedance variation and voltage droops. Impedance refers to the opposition to the flow of electrical current in a circuit and is characterized by resistance, capacitance, and inductance components. When a circuit switches between different states, such as transitioning from idle to active or from low to high current demand, the impedance of the circuit can vary dynamically, leading to voltage fluctuations known as voltage droops. Voltage droops occur due to the transient response of the power delivery network, PDN, to changes in load current. During circuit switching events, sudden increases in current demand cause voltage drops across the impedance of the PDN, resulting in temporary reductions in supply voltage levels. These voltage droops manifest as rapid fluctuations in voltage over time, with the magnitude and duration of the droop depending on the characteristics of the load, the impedance of the PDN, and the transient response of the voltage regulators. Causes of voltage droops. Several factors contribute to voltage droops in switching circuits. 1. Power supply impedance. The impedance of the power supply and distribution network, including the resistance, inductance, and capacitance of power traces, vias, and decoupling capacitors, affects the transient response of the PDN to changes in load current. Higher impedance leads to larger voltage droops and slower transient response times. 2. Load transients. Sudden changes in load current, such as when digital circuits switch between logic states or when active components turn on, off, induce transient voltage fluctuations in the PDN. These load transients create temporary imbalances between supply and demand, resulting in voltage droops until the PDN stabilizes. 3. Decoupling capacitor effectiveness. The effectiveness of decoupling capacitors in providing local charge reservoirs and filtering high-frequency noise influences the magnitude and duration of voltage droops. Inadequate decoupling capacitance or poor placement can exacerbate voltage droop effects by limiting the ability of the PDN to respond quickly to load changes. Effects of voltage droops. Voltage droops can have several adverse effects on circuit operation and performance. 1. Signal integrity degradation. Voltage droops can lead to signal integrity degradation by causing signal distortions, timing jitter, and noise susceptibility. Rapid fluctuations in supply voltage levels can introduce noise into signal lines, leading to data errors, timing violations, and signal integrity issues. 2. Circuit malfunctions. Large voltage droops can result in insufficient supply voltage levels, causing circuits to malfunction or operate outside their specified operating conditions. In extreme cases, voltage droops can lead to circuit latch-up, transient faults, or permanent damage to electronic components. 3. Power delivery issues. Voltage droops can impact power delivery by reducing the effectiveness of voltage regulation mechanisms and increasing power dissipation in active components. Inefficient power delivery can lead to decreased circuit efficiency, increased power consumption, and reduced battery life in portable devices. Thanks for watching. Please like, share, and subscribe.